Hi everyone, my name is Itai Zilberman, and today I want to present our work, Qualitative Belief Space Planning via Compositions, which was written by me and Professor Vadim Indelman. Let's start by introducing qualitative approaches as a general framework in robotics tasks. In these approaches, in contrast to the metrical, the environment that robots poses are tracked using coarse relative geometrical relations known as qualitative spatial relationships, or QSR in short. For instance, consider this very simple living room scene. Based on only two objects, we can fix a local coordinate system and discretize space into a finite set of disjoint regions, called qualitative states. Then we can locate a third target object in terms of these states. For example, we can describe the location of the flower pot relative to the sofa table frame as middle right, and so on. This coarse manner of reasoning about spatial information is potentially more noise robust and thus suitable for low-cost platforms equipped with poor sensors. An essential component in the qualitative approaches is the composition operator, enabling spatial information propagation between different triplets to infer new ones. More specifically, given two source triplets, we can conclude a third one using some very simple geometric reasoning. In this work, we propose a first-of-its-kind qualitative belief space planning algorithm, or qualitative BSP in short. That is, we developed a novel formulation of the well-known belief space planning algorithm, however, that considers a qualitative framework rather than a metric one. In addition, we incorporate compositions within our approach to further improve results. Finally, we propose a novel cost function that can measure metric distance using qualitative information. Before explaining our algorithm in detail, let's state the problem we aim to solve. First, we define a belief. So consider K as the current time step. The belief is defined as a posterior distribution over the qualitative states of the robot, landmark triplets, and frame scales. By frame scale, we mean the global metric distance between the two landmarks that create the frame. This is a new concept that was developed in our work. Next, we consider a future horizon of L look-ahead steps and define the objective function as the expected cumulative cost with respect to these L steps. Our aim is to find an optimal sequence of actions or plan that minimizes the objective. Now, how do we approach this problem? Planning in the belief space is traditionally done in two stages. In the first, we construct a belief tree, which reflects the propagated belief considering various possible future developments. Each branch in the tree describes a future development of a single candidate plan. In the second stage, we extract an optimal plan based on the constructed tree. The focus of this work is on the first stage. So we shall now explain how to construct the tree. Mathematically, in each construction step, we need to update the belief considering a specific candidate plan or a specific branch. To infer the belief at time step t, given the one from the previous time step, t minus 1, and given a candidate plan and measurement, we use the updating rule shown here. In the next few slides, we shall explain intuitively the different components of this updating rule. So the first component is the qualitative motion model, which evaluates the probability of the robot to reach any of the possible qualitative states, considering the specific frame, as a result of taking the candidate's qualitative action. The second and third components are the measurement and association models, which evaluate the probabilities of observing a specific measurement involving a particular triplet of landmarks. Note that in these models, we need to evaluate the robot's range of view, which is the green circle in the figure, in global terms. And to do so, we use the global frame scale, which was mentioned before. Finally, the last component updates the belief with a candidate link action. The link action allows the robot to switch between different frames. Even though it is considered an action, in practice, the robot doesn't make any actual movement, but only translates its self-location from one frame to another. Okay, so this was the basic updating rule. But so far, we didn't use compositions at all. So how can incorporating compositions within our approach can further improve it? Firstly, it allows us to deal with a wider range of scenarios. That is, in some cases, a plan can be found only via compositions. Secondly, we can find better plans using compositions, namely, plans with lower objective. Mathematically, to incorporate compositions, we need to add one more term to our updating rule. The role of this new term is to compose a new triplet and add it to the belief. With this newly composed triplet, the robot can consider more links in planning sessions and potentially find better plans or even exclusive plans sometimes. So we tested our algorithm on over 2,500 different scenarios, and we can see that it works well. However, when we use compositions, it works even better, which is not surprising. We invite you to check out the paper for some more specific running examples. That is all, so thanks for listening and enjoy the rest of the conference. Bye-bye.